I think we'll make a start, and as people arrive, we'll just let them into the room. I want to thank everyone here for coming here today. Before we begin this seminar, I want to start by showing my respects and acknowledging the people who are the traditional custodians of this land, the Darug and the Aurora people, of elders past and present, on which I am hosting this seminar. And just as we begin, I also want to remind everyone of the structure of our seminars. Today's speaker will be speaking for 40 minutes, and then we will have 15 minutes or so at the end for questions and answers. So if you do have questions during the talk, post them in the chat. I'll record them, and depending on whether or not you're present at the end of the seminar, I will either pass on your question or you can present it yourself. But yeah, hold all questions. But yeah, if you do have a question, make sure to post that in the chat. So today's speaker for the CAR seminar is Dr. Aranima Malik from the University of Sydney. Dr. Aranima Malik is an academic at the School of Physics and the Business School. Her research is interdisciplinary and focuses on the appraisal of social, economic, and environmental impact. She's undertaken assessments for health systems and other economic sectors, and her talk today is on sustainability supply chain assessments in Industrial Ecology Virtual Laboratories, which sounds incredibly interesting. So I'm fascinated to hear what you have for us today. Just leave this share, so you should be able to you should be able to share your slides now.
Thanks, Nathan. Hello, everyone. I'll just share my screen. So as Nathan mentioned, I work at the University of Sydney. I have a joint appointment with the School of Physics and a Business School, quite an odd combination. But essentially, my work revolves around doing sustainability supply chain assessments. So in the talk today, I will talk about what I mean by sustainability in terms of the work that we are doing as a group, myself and the members of the group, and particularly some examples of the work that we've done in health systems and other sectors. So when we do sustainability supply chain assessments, we like to come up with some indicators for assessing, let's say, progress of different sectors towards sustainable development goals, or to just capture impacts indirectly in supply chains. So some of the indicators that we have developed as a group here at the School of Physics and the Business School are environmental indicators, which are on biodiversity threats. So essentially measuring threats in supply chains linked to consumption of items. So if we have a health sector and that health sector requires inputs of electricity or other consumables, equipment, for example, then what is the supply chain impact of that consumption? And that supply chain impact can be quantified in terms of biodiversity threats, greenhouse gas emissions, energy use, nitrogen emissions, air pollutants, so a range of air pollutants, water, waste, land. So these are some of the environmental indicators that we use in assessing impacts in supply chains. Social indicators are fairly new that we have been developing that take into account poverty in supply chains, corruption in supply chains, employment, which is considered a positive indicator, so job creation in supply chain, child labor, so if there are children working in the supply chain, for example, in the construction sector or in the textile sector, so that's another social indicator. Then we have income inequality and occupational hazards. So occupational hazards takes into account fatal and non-fatal accidents in supply chains. For example, if there is European Union consumption, which is a recent study that we worked on, then consumption of items, for example, textile, clothing, and footwear, if that production happens in countries around the world, what are the fatal and non-fatal accidents resulting from them? And modern slavery is another indicator that we have been working on developing in the social sphere. And then we have some economic indicators. When we do supply chain assessments, I would just like to start by giving a very simplistic sort of an example. For example, consumption of coffee. So if we have coffee consumers, of course, around the world, but I've just put coffee cups, random spots on the map. So we have coffee consumers around the world. So they are consumers, but where exactly are the coffee beans produced? So they are could be produced, if we are consuming coffee here, sitting in Australia, and the beans are coming from South America. Then going from a supply chain perspective, looking at indirect impacts, we can identify which species are getting affected by consumption of this particular product. So in a way, sustainability assessments that we undertake, they try to link producers, where are the products being manufactured, and consumers. So looking at the supply chain linkages. And one of the famous papers that came out from one of my colleagues, Manfred Lenzen, was looking at biodiversity threats. So this was published a number of years ago, looking at biodiversity threats on a global scale. So we, in Industrial Ecology Virtual Laboratories that I'll talk about in a minute, we're able to develop global databases that capture international trade between different countries and different sectors, and also subnational databases. And we've used them both for doing sustainability assessments. So in this particular study, the authors used a global database of international trade linking production and consumption in different parts of the world to see what are the drivers, so what countries in terms of suffering threats and also driving threats. So we have a number of lines. So Malaysian species threatened by foreign consumption. So if you identify that we're interested in Malaysian species and those species threatened by foreign consumption, then we can pinpoint who exactly is driving impacts in Malaysia. So Germany, for example, is driving 9 threats. We're driving 14 threats, and they could be 14 different types of species. UK is driving 9, China is driving 11, for example. On the flip side, if we want to see, well, picking on a country, so let's say German consumption, all species threats driven by German consumption, then we can again assess the supply chains to see where exactly are the impacts happening. So China, in this case, suffers 11 threats, for example, for satisfying consumption in Germany. Russia suffers 13 threats, and so on. So this is an example of a supply chain sustainability assessment that takes into account the biodiversity indicator. When we assess supply chains, we start off by consumer demand, and we look upstream to see what is the upstream supply chain. For doing this for the health sector, as we've done for Australia's healthcare system and New South Wales healthcare system, and also at a global scale, we considered all the inputs that were bought by the healthcare sector. So the healthcare sector, we divided that into a number of sectors: hospitals, pharmaceuticals, dental services, and so on. And we looked at the supply chains of each of them. So essentially, it starts off by looking at demand for products. For satisfying demand for products, sectors in the economy, they need to supply inputs for satisfying that demand. If these sectors in the economy, and to keep it really simplistic, I've kept food, resources, goods, energy, and services, but the input-output tables that we use, they encompass a range of sectors. So in some cases, if we're looking at a global table, we have more than 15,000 sectors. For the Australian table, it could be around 300 or so. But to keep it really simplistic, on this diagram, I've used aggregated terms. So food-related sectors or resources-related sectors, goods, energy, and services. In essence, what I'm trying to communicate is that if you have a consumer demand, be it for any sector in the economy, then for satisfying that demand, other sectors in the economy, they need to produce a particular output for satisfying the demand. And these sectors in turn would need to interact with the rest of the economy so that they're able to produce an output that they can then send on to their, for satisfying consumer demand. So we have in a way an upstream supply chain tree, which keeps going like this. So we call this the supply chain tree because it sort of expands, starting from consumption of goods and services and then looking at their upstream indirect supply chain. We can also identify impacts for specific supply chains. So if there is an insurance company, or it could even be university, we've done this for universities as well. So if we have a university, of course, we use a lot of paper in printers. So where exactly does that come from? Wood, machinery for wood industry, steel for machinery, iron ore for steel. So just unraveling every link in the supply chain to see what is the impact of that specific node or specific link. So that is the kind of the research that my colleagues and I do at the ISA group. So I'm part of the Integrated Sustainability Analysis group at the School of Physics and Discipline of Accounting at the Business School. So how exactly do we do these assessments? We use large matrices that capture inter-industry relationships, because if we want to assess how two sectors interact with each other and how they come about in a particular sector's indirect supply chain. So if we have a health sector that we want to assess the indirect supply chain for, then we need to know, well, the health sector needs electricity. Where does electricity come from? For producing electricity, you need machines, or if it's fossil fuel based, then you need input of coal, for example. Then coal mining sector, you go a layer up and look at the coal mining sector. What does the coal mining sector need for mining coal, and just keeps going upstream. So for unraveling these interactions, we need a matrix that captures interactions between different sectors. And we call these input-output tables. And these input-output tables that we use are global input-output tables. They're national input-output tables or sub-national input-output tables. And this is essentially a heat map of a large multi-regional, so containing information on more than one region, so Germany, France, Australia, so global region as in country level information, and it has 15,000 rows and 15,000 columns, and these color codings are basically values transformed into a heat map. So for doing supply chain assessments, we construct these in so-called Industrial Ecology Virtual Laboratories. And the background of this is that we need information on primary sectors, which could be extraction of raw materials, for example, mining, fishing, agriculture, secondary sectors, production of finished goods, so cars, food, clothes, shoes. Depending on the input-output table, some can be really detailed. So Australian input-output tables, for example, they're fairly detailed in comparison to input-output tables of some island economy. So Norfolk Island's input-output table only has 18 sectors. So the sectors are aggregated for that small island. For large economies, we have good detail on disaggregated input-output sectors and tertiary sectors. This technique, just to give a bit more background on how this technique sort of came about, and we've adopted it for doing supply chain assessments and are now coming up with industrial ecology virtual laboratories that allow us to construct customized input-output databases depending on the application that we want to use it for. So this came about in 1930s by Vasily Leontev, who got a Nobel Prize for coming up with this technique, because essentially, if we do a life cycle assessment, depending on the question, we're not always able to assess impacts at every upstream node, but we are able to do so if we use an input-output technique coupled with life cycle assessment data, so hybrid LCA, for example. Essentially, this technique involves working with input-output tables. So there are a number of input-output tables that we work with, and they're structured as follows. So we have a so-called intermediate demand matrix, and this intermediate demand matrix captures different industry sectors. So mining, electricity, health system, all these sectors would feature in the intermediate demand matrix and the interactions between those sectors. So by interactions, I mean, if we have a health sector in our input-output table, using that health sector's column, we can find out, well, how much input is the health sector getting from the electricity sector? How much input is the health sector getting from an equipment sector or the food sector, for example, beverages and other sectors of the economy? So that is the kind of information that we can gather or take away from the intermediate demand matrix. The final demand matrix gives us information on our consumption, so households. So if we go to the shops to buy a particular item, our consumption it features in the final demand matrix. The value added matrix gives us information on wages and salaries. So we have all these different sectors in the economy, and we have people working for those sectors. So what are the wages and salaries? That is this kind of information that we can get from the value added matrix, or information on taxes, for example. Luckily, we don't have to construct these tables from scratch, because they are sort of made by the ABS, which is the Australian Bureau of Statistics, if you're interested in an Australian input-output table. And across the world, every country sort of has a statistical agency that puts together data from different businesses to make these input-output tables. So our research mainly involves taking input-output tables. So if we are interested in doing a national study, like we've done for Australia's healthcare sector, so if we're interested in doing a national study, we obtain input-output tables from the ABS, their time series. So they put them out on a regular sort of a basis. So we get an input-output table, and we link these tables with different indicators. So on the first slide, I had a range of environmental indicators, a range of social indicators, and a range of economic indicators. So essentially, these input-output tables from the ABS, they hold economic data on how different sectors of the economy interact. And then we have information on indicators, and we can obtain those, for example, greenhouse gas emissions from National Greenhouse Gas Inventory, or if we're interested in global emissions data, we get that from the ADGAR database. IUCN, International Union of Conservation for Nature, we use that website for getting information on biodiversity threats. Food and Agricultural Organization or International Labor Organization for employment data. Depending on the indicator that we're interested in, we obtain data from a source and we link it with an input-output table using concordance matrices or proxies for linking data, which is in a specific classification. An input-output table classification is mostly sort of, in many cases, different from the classification that we get from the data that we get from other sources for indicators. So we have to sort of match the data with the classification of input-output tables, and then we're able to run supply chain assessments. These industrial ecology virtual laboratories that we've been developing, the aim of this development is to bring together researchers from different universities. So the project started in 2012. We obtained some funding from Nectar, and using that funding, we collaborated with about 7 Australian universities to come up with a prototype, a working platform, a collaborative platform where researchers from different universities contributed data based on their expertise. So we had, for example, a person with expertise in water systems contributing data on water use, someone with expertise in energy systems contributing data on energy use. We had people contributing data on air pollution, greenhouse gas emissions. So we all sort of came together to have a collaborative cloud computing platform which can hold information about different indicators and the capability of constructing customized multi-regional input-output tables. Because the data that we get from ABS, the economic data that we get from ABS, it has a fixed resolution. So we're not able to play around with the resolution if we just obtain the table from the ABS. But in this virtual reality platform, or Industrial Ecology Virtual Laboratory platform, we've come up with a sort of a methodology for constructing subnational tables, for linking those to different indicators. And if you're interested in finding out how it works, you could log in. So it's ielab.info. So ielab.info. That is the link for the website, and the interface that it sort of works on is based at the School of Physics at the University of Sydney. So we have a MATLAB-based development platform that we have now put online as well for people to log in and take a look at. So we have IE Labs for Australia. This IE Lab Australia lets us construct tables with specific information at SA2 level. We have IE Lab for China, so we can have a table with different regions in China. if there is an application that is based on a specific region in China, for example, Beijing, we can have an economic table for that region so that we're able to assess supply chains in that region. We have IE Lab for Indonesia, again, for different regions in Indonesia. We have IE Lab for US, Taiwan, Sweden, Japan, and we have IE Lab Global, which works at a global scale. So if there is an application, for example, the biodiversity threats study, then we need data on different countries, but not necessarily at a detailed regional level. Then we can work with IE Lab Global. We're also working on coupling these IE labs. So for example, if we want to trace supply chains from regional New South Wales to, let's say, EU or the US, then we can couple the subnational table from IE Lab Australia with the IE Lab Global table, so that in one table we have New South Wales instead of Australia. We have New South Wales, Victoria, or different states, and we also have data on countries. And we call these nested multi-regional input-output tables, because in a way we've nested a subnational table, a subnational detail, regional detail. It doesn't really have to be at New South Wales. We can break it down further. So there it's at SA2 level. So we have a nested table that has not only global data for different countries, but also subnational data. And these nested tables can only be made for the national IE labs that we have. So we can have a nested table for Australia, China, Indonesia, or any of these 4 countries. So some of the applications of supply chain assessments. So I've come up with a couple of examples. There are different applications, some for healthcare systems, some for emission related assessments at a global level. So I've kept it very broad. So hopefully you would find it interesting. So some of the applications, the starting point for using data from the IE lab is to, again, as I mentioned, couple it with an indicator. So we need to integrate global data sets. In addition to the IE lab platform, we also have another platform, which is worldmrio.com, and we call this the EORA database. So we've called it EORA based on the traditional owners of the land. So worldmrio.com, or the EORA database, that is the database that includes information for 189 countries, and that was the one that was used in the biodiversity paper and a number of other papers that have come out from the data that we've put together on worldmrio.com. So the starting point is to have a global trade model. If we want to assess international supply chains, we need information on imports and exports. So in these tables, we have countries and sectors in the rows, and we have countries and sectors in the columns. And the same countries and sectors feature in the rows, and in the same order they feature in the columns. So in a way, we're able to see not only domestic trade or domestic interaction, domestic production and consumption within a country. So Australia, if that's the first region, we can see how the domestic economy works. But we can also see, if the first country is Australia and you have all other countries listed here, we can see, well, what is Australia importing from all other countries in the world? Or what is Australia exporting to all other countries of the world? So we have export and import data in one big matrix that we can use for assessing supply chains. So these are what we call large matrices that capture inter-industry relationships at a global scale. And worldmrio.com, as I mentioned, has data on 189 countries. IE Lab Global came out of worldmrio.com, and we've expanded the country list. So for IE Lab Global, we have coverage for 221 countries of the world. And this is what we call a multi-regional input-output table, as the name suggests, more than one, data on more than one region. After we have data on more than one region, economic data on imports, exports, and how the sectors and the countries interact, we also then obtain data on indicators. So water use, employment, income, carbon dioxide emissions, or any of the other indicators that I had in my diagram. So depending on the application, we focus on an indicator. So this was published a number of years ago. For some of my applications, I've used papers that have been published a while ago and some of the recent papers, just to give a breadth of the kind of our research interests as we work in supply chain assessments. So this paper was published a while ago, and this only focused on greenhouse gas emissions. So in terms of emissions, then we needed to have data on international trade, so that big matrix capturing export information, and data on emissions. In this study, we were interested in looking at the role of outsourcing in driving global carbon emissions. So outsourcing is basically a phenomenon where you have a country exporting. Initially, the goods and services are being produced in a country and they're used for domestic consumption. But to reduce their production-based emissions, as in emissions within their country's boundaries, countries outsource so-called dirty production to other countries. So we've been seeing a phenomenon where you have developed nations outsourcing their emissions-intensive production to some of these developing countries. So in simple terms, it just means that you have developing countries producing energy-intensive commodities that eventually end up in developed economies for final consumption. So we call these outsourcing, this process of outsourcing that is driving emissions at a global scale. So we have two rows here. So the top row are emissions and the bottom row are emissions as well. And you would see that you have different bar graphs. So we wanted to see specifically what is driving these emissions, whether it's efficiency, whether it's production recipe, which essentially means changes in the way things are produced, final demand composition, again, changing the composition of final demand in terms of the demand for our goods and services, final demand destination, so changing the destination of where things end up. Affluence is consumption per capita, and population growth. So we wanted to see, well, what is driving emissions? Is it population growth at a global scale, or is it our consumption at a global scale, or is carbon efficiency having any effect at a global scale? So really what we notice is that, of course, efficiency has improved over time. So at the bottom, we have a time scale from 1990 to 2010. Efficiency has improved. That's why we have these green bars, which are negative. So improvements in efficiency have resulted in a reduction in emissions, but at the same time, our consumption has increased, which is red. So these are these red bars. So this increase in consumption or affluence has been a key factor in driving emissions at a global scale. So that was the key sort of a takeaway of this study from a supply chain perspective. The supply chain perspective in this study was that we looked at every country, and we've included only a couple on this slide, but we looked at each of the 189 countries and we assessed their supply chains to see the contribution of the domestic production and consumption system and the contribution of their imports in terms of emissions happening elsewhere, but imports ending up in a location. So considering those aspects, we sort of deduced that, you know, outsourcing is happening at a global scale, and the developed world is mostly driving it. A different study that we carried out again on a global scale, this time in collaboration with the United Nations Sustainable Development Solutions Network, was to look at a social indicator. So the first application that I introduced, that was an environmental indicator. Here we were interested in looking at a social indicator, and specifically fatal and non-fatal accidents. So I have here skulls. So these are fatal accidents happening in different parts of the world. And then I have here ambulance, which is non-fatal accidents. So non-fatal accidents, unfortunately, people ending up in hospitals, but fortunately not losing their lives. And unfortunately, here people losing their lives because of consumption in the EU. So in this study, my collaborators were specifically interested in looking at European Union's consumption of textile supply chains. So we isolated the textile sector for all the different countries in EU, and for the demand for textiles in EU, we scanned the upstream supply chain. So if you remember my supply chain tree, I had the consumer demand at the bottom. So for that consumer demand, if I look at textiles and the textile demand for each of the different countries in EU, then I can isolate the supply chains specifically for that sector. So of course, in our input-output table, we have data on food demand, we have data on demand for electronics, energy use, textile, clothing, but we were only interested in textiles, so we isolated those supply chains. And on a global scale, we wanted to see, well, again, spillover impact. That is another term that we've started using, which is sort of synonymous to outsourcing, but outsourcing is mostly used for emissions, and spillover impacts is more of a broad term that we use for any sort of an indicator. And it essentially means the same thing, that we have consumers sitting in one location with their demand for goods and services, and the impacts are happening around the world. So in this study, because of our interest of collaborators, we focused on EU consumption, but in essence, it can be done for any country of the world. So the key takeaways were, fatal accidents as one indicator and non-fatal accidents as another indicator. So fatal accidents for satisfying EU's consumption of textile products. We have fatal accidents happening in a number of Asian economies, and also for satisfying EU's consumption of textile products. If you look at non-fatal accidents, then we again see some of the Asian economies pop up in terms of the impact. Another application of Industrial Ecology Virtual Laboratories and these input-output tables are for quantifying impacts of disasters. So if we consider COVID-19 as a disaster, and we look at a supply chain perspective for COVID-19, then we can see, well, of course, COVID has had an impact when it comes to environmental side, social and economic. And if we start to put a number to it, we sort of did the study when we had the first wave. So it was published about a year ago, and we're still in the middle of it. So about a year ago, we thought we'll put a time scale. We'll say, okay, we're going to collect data until May 2020 around the world for impacts due to COVID in terms of reduction of output. So we had the first sort of lockdowns put in place, and we looked at different countries in the world to see what industries were affected directly by COVID-19 and the measures that were put in place. And based on that information, we integrated data on losses, direct losses. So for example, if we're interested in looking at the manufacturing sector's loss of output in China, then we go to the gray literature or newspaper articles, whatever information that we can find online for that specific country. We obtained that data and fed that into an input-output table to see, well, what are the supply chain impacts. And as we have heard in the media already, so of course, we had impacts all across a range of sectors. So we had manufacturing, see a reduction in output, and of course, transport and tourism, service sectors, trade. So all across the world, and we've aggregated these regions. So we had China, rest of East Asia, rest of Asia, Middle East, and OPAC, and other countries. So again, an application where we've used an industrial ecology virtual laboratory platform for a disaster study. We've also done this at a national scale. So this was a global study. So we needed a global table. So this was IE Lab Global that we sort of worked on because we needed global data for different countries of the world. But if we are interested in a disaster which is much closer to home, then we need data from IE Lab Australia, because then we would be interested in identifying different regions of Australia and how the disaster impacted those regions. And that's where the fourth application sort of comes into play. So this is again disaster assessments, but this time focusing on Cyclone Debbie, which hit parts of Queensland a couple of years ago. And we used data from IE Lab Australia. We developed a multi-regional model, again, a big matrix. But this time information on different regions of Australia, because that's what our application was about. So different regions of Australia, and specifically Queensland broken down into a number of regions, because that was where the disaster sort of hit, because cyclone hit Queensland, and we wanted to keep Queensland disaggregated in terms of our resolution in the table. So we had these regions in the table that we constructed. And we looked at two indicators. We looked at loss of employment, so job losses, and loss in value added. And this is the finding that we obtained after running the model by feeding in specific information about direct losses, as in if when the cyclone hit here, then farms were destroyed, then what was the loss in output. So all that direct information that we were able to gather from industry reports or grey literature, we fed that into the model and we ran the supply chain assessment to see, well, indirectly, because of the interconnected supply chain network, it was not just parts of Queensland that were affected by this cyclone, but the effects were felt all across, pretty much in every state. So this was sort of, again, an example of the importance of looking at the upstream supply chain when it comes to disasters or disruptions. So it's similar to the COVID-19 study, but that was at a global scale. We wanted to see the disruptions in supply chains at a global scale. And in this study, we wanted to see how the different states of Australia are impacted in terms of losses. So the color shading sort of gives an indication of the measure of impact. So of course, more impacts here because that is where the disaster hit. So there were direct impacts, immediate impacts, but then this region sort of trades with other regions across Australia, and in those supply chains, we had a variation in the impacts being felt, and that is depicted in the colors. And then in addition to doing assessments for specific indicators, for example, environmental, as in the first application, social, as in the second application, or a range of indicators. So I forgot to mention in the COVID-19 study, we coupled a range of indicators. So we had consumption losses, we had income losses, employment losses, where we had, so we consider income as an economic indicator, employment as a social indicator, and 3 environmental indicators. We wanted to see greenhouse gas reduction because of reduction in output due to COVID-19, PM 2.5 reduction, and then we have air pollutants as well as another indicator. There's another stream of research that we have been working on by integrating bottom-up data with these top-down models that we've developed. So hybrid life cycle assessments at a national scale. So I mentioned we've done some work for Australia's healthcare sector. And for this was published in 2018, so a couple of years ago. We collected specific information on health expenditure for the different categories from AIHW, Australian Institute of Health and Welfare. So that was our bottom-up data that we collected because we were interested specifically in that sector, and not just an aggregated healthcare sector, but we wanted to break it down according to hospitals, public and private. We wanted to look at specialist medical services or GPs or dentistry. So according to data from AIHW and following exactly their definitions of how they sort of defined these different categories, we got expenses data, which we then fed into an input-output table, a national input-output table, because we wanted to do this at a national scale. So we only had Australia in our input-output table and a range of sectors. So we fed this information into the input-output table to see how Australia's healthcare sector interacts with other sectors in the economy, and we carried out a hybrid life cycle assessment. So in a hybrid life cycle assessment, we consider the entire supply chain from using input-output tables. But in addition to that, we use specific data on the industry or the sector of interest. So in a way, if we're doing a conventional life cycle assessment, as studies have shown, we have to often draw a boundary. And this ends up in studies missing some of the impacts in the supply chain. So when you have to draw a boundary, then you miss some of the upstream indirect impacts. But in a hybrid approach, you have, as we say, best of both worlds. We have completeness because we can assess the supply chain, and we have specificity because we're able to gather specific information. So there are advantages of using both input-output and LCAs, and we can combine this into a hybrid approach, as many researchers around the world have now started doing. So in this study, we used the emissions indicator in the IE Lab Australia, and we looked at the carbon footprint of Australia's healthcare sector. The key finding was that it contributes about 7% to Australia's total footprint. Again, 7% is broken down into a range of sectors. So we have public hospitals, private hospitals, specialist medical services, and other sectors. Following on from this study, we went regional with IE Lab Australia, and we focused on New South Wales because we wanted to see, well, we have a figure or an understanding of how the impact sort of come about for national healthcare sector, and New South Wales Department of Planning, Industry and Environment, DPIE, they were interested in having estimates for New South Wales. So we did the study again, this time using 3 indicators, because in addition to emissions, we also thought it would be interesting to look at water use in the healthcare sector and waste, which is again a key indicator in the healthcare sector. So for these 3 indicators, we constructed a sub-national table, and these were the regions that we considered. We had New South Wales specifically in our table that we obtained from IE Lab Australia. We had other states sort of in the table as other regions. And we kept other states separate because we wanted to see how New South Wales sort of interacts with other states. So we had a table, a multi-regional table for Australia, and we had 3 indicators. And these were some of the findings. Again, we got data from AIHW. I find that a really great source for getting information on health expenditure, and they have information at state level as well. So the bottom-up data for this study was obtained from AIHW. It was expanded to a multi-regional context and for a range of indicators. So as expected, the key contributors are hospital services, pharmaceutical products, and medicinal goods. And in terms of unraveling the upstream supply chain, so again, with the supply chain tree going from demand by the healthcare sector and other sectors sort of producing goods and services for satisfying that demand, we can have the layers of production put on the x-axis, the indicator on the y-axis. For greenhouse gas emissions, we can sort of start to see, well, which sectors are responsible for emissions. So mining, because electricity is a key input in the healthcare sector. So the mining sector plays a key sort of a contributor in terms of hotspots of impacts, and this is cumulative. So these would be the total impacts broken down according to different layers of production. So the health system in New South Wales, we found, was responsible for just over 6% of greenhouse gas emissions, 4% of water use, and 8% of waste produced in the New South Wales economy. And just to finish off, so this was my last application, that I think leaves time for questions as well. So IE Labs, as we've been developing over a number of years, as I mentioned, we've been doing a range of studies at a regional level for IE Lab Australia, for example. We've done a number of studies using IE Lab China, IE Lab Japan, but I only have picked out a couple of them to just showcase the kind of work that we have been doing in terms of supply chain assessments. And I think I'll leave there to have your comments. Nathan, do I pass it back to you?
One sec. Thank you very much for that. For a start, that was excellent. Really interesting talk. And yeah, there we go. And we'll open the floor up for questions if anyone has any.
Arunima, hi, it's Jeff Morgan here. Thanks for that. It was really fantastic. It's amazing, the sort of scope of work that you're doing. I was interested in slide 16 that you had, where it had specific emissions of air pollutants broken down. Just wondering where you got that from. So you've got the sort of the emissions of PM 2.5 in, is that kilotons or something like that?
Yep. So we got the sector level data from the EDGAR database.
Right. And that's got emissions in it, doesn't it?
It has emissions and a range of categories for emissions. So a range of air pollutants, greenhouse gas emissions broken down into just CO2, methane, N2O. So there are about 20 odd categories with specific data for each of those, and in a way, footprints can be calculated for either of those categories, because we've now updated the database in the IE lab and sort of have integrated this information in the global IE lab. So this is IE lab global, yeah.
And you can link those to various sectors like mining and manufacturing globally.
Yes. Yeah. So we've in the linking process that we carry out, which is part of this integration of accounts. So we have, let's say we have an input-output table at a global level, and we have EDGAR or emissions data on air pollution for a range of categories at a global level. Then when we do the linking, then we have emissions information linked into all the sectors. So we have a value for agricultural sector, mining, manufacturing, all across essentially.
Fantastic. Look, sorry, what's that acronym you're using? EDGAR?
EDGAR. I'll just maybe type that in the chat.
Thank you. Great. Thanks very much, Aranima. It sort of generates a lot of ideas about things that could be done. Thank you.
And thanks, Michael, for your comment in the chat as well.
Do we have any other questions?
One of the other questions I have, Aranima, is I know that in New South Wales, I think the way the health system works, it's very much a sort of regionally based system. Mm-hmm. And there are sort of chief executives of regional health department, of health department regions. And they, I think more recently, have got sort of sustainability put onto into their contracts, I think. Mm. And so to be able to disaggregate that one you've done for New South Wales even further would be, I think, something that they'd be very interested in. Is that possible with your work?
Yeah. It's great that you raised this point, because we've been having conversation with Western New South Wales Health, and they are interested in having such an assessment done. It is possible to disaggregate New South Wales into different sub-regions. So yeah, definitely. So the answer is yes, and there is some talk as well. As you mentioned, I think there's a fair bit of interest now in this space.
Yeah, and I noticed that's just been accepted, that paper. That's great. Thank you.
We have a question from Rachel. Rachel, if you'd like to take the floor, you can ask it if you'd like.
Thanks, Nathan. No, I can't speak now. I've been on quiet for so long. Thanks, Aranima. What amazing work you're doing. My mind is just kind of a bit blown out by the breadth and depth of it. Just from a personal perspective, because some work I've done for CAR, part of the lab, will you be examining, this is just one example, the sustainability impacts of solar panels in the long term? As we know, the increased uptake of solar panels on residences. So thinking about the production of the panels, the energy production that feeds back into the network and all that comes with that. But then the final e-waste management. Is that something that you look at or have any thoughts on?
Yeah, thanks, Rachel, for your comments and the question as well. We've done some work for a range of renewable energy sectors. So biofuel is one of them, where we've looked at production, energy production, as in production of feedstock, and then energy productions from a supply chain perspective. We've also done it for wind energy. It's possible to do it for solar energy as well, so solar panels to be specific, but I don't think we've specifically looked at this yet. So this could be one exciting research question to explore as well, is how I also put it.
Oh, fantastic. Thanks. I look forward to hearing that. Hopefully you'll come back and tell us about it.
Next time.
Thank you.
Hi, it's Christine here. Did you say, did you just say that you have looked at wind farm components?
Yeah, so my colleague has done some work in looking at wind energy and the impacts from a supply chain perspective, and also from an energy return on investment perspective. So energy in, energy out, and the payback period. So those kind of determinants of how sustainable are wind farms. So we've done some, and that was based on input-output tables as well. So it would be very much possible to do sort of a similar sort of a study looking at solar panels. So, but I don't think we've looked at that yet, looked at solar panels yet.
Okay, and what were the results of the wind farm study?
The payback period, if I remember correctly, was done this was done actually more than 20 years ago. The payback period was a couple of months. So the conclusions are that wind energy is sort of, from a supply chain perspective, one of the most sustainable ones out of all other sources of renewable energy. There might be some studies out there that have used input-output tables for solar panels in some sort of context. I'm not sure. I haven't explored specifically because that's not particularly my area of research, but I've been focusing on biofuels. And for biofuels, it's been done for a range of regions, I would say, yeah.
Thanks.
We've got time for one or two more questions. Does anyone else have any? I actually have one. So I don't know if this is way beyond the scope of projects like this, but have you considered doing, or is it possible to use these models to actually play around with different supply chains to see their impact? So for example, if you, thinking back to that really early slide about the impacts on biodiversity and looking at supply chains in different countries, is it possible to say if we move a supply, if we change the supply chain from Germany to another country, what would those impacts have on biodiversity, or is that beyond the scope of projects like this?
Yeah, that's a really interesting question. So I think what you're referring to is substituting the supply chain to see how the impacts would sort of vary. There haven't been much studies done on this, but I would imagine that it would be possible, because essentially if we have this matrix and we have a production recipe, we call it a production recipe, just like we're baking a cake, for example, all the inputs of the different sectors need. So if we make tweaks to that production recipe and rerun the model, we would be able to see, well, what sort of impacts do we get for this alternative scenario? Specifically for substitution effects, we haven't done this, but we've made comparisons across energy systems in the sense that we've taken the traditional fossil fuel-based production recipe and a production recipe for bioenergy, where we tweaked the different values in the table, and we ran it to see, well, what would be the implications for emissions in the supply chain. So we did see a reduction in emissions. What would be the implications for jobs in the supply chain? If we reduce, for example, fossil fuel use, then there'll be job losses, but then can they sort of be complemented? If we have more bioenergy, for example, could that take it up in terms of the job losses and creation, but like balance it out? So it's been done for these. specific studies, I would say, but at a global scale, it would be possible to do such a study as well, looking at Germany or other countries of the world and just changing their supply chain composition.
Very interesting. We've got time. I'm going to give time for one more. So if anyone else does have a question, please speak now. All right, well, in that case, I think we will end it there. Thank you very much for your presentation today, Aranuma.
Thanks for having me.
No worries, thank you. And yeah, we'd love to see more of your work in the future and definitely be following you in this space.
Yep. I mean, Jeff and I, we're already working on a paper on, wood heaters. So maybe next round we'll have the findings of that.
I'd be very interested to hear that. Thank you so much again. That was really, really great.
Thanks, everyone.
Thank you. It was fantastic.
Thank you.